Now, in what do we do in regularization? Let's now speak more broadly about regularization before we focus on norm control, which is what we're going to do, and it will lead to ridge regression. In regularization, we shrink the size of this hypothesis space. We restrict it in some way. We shrink its size. How can we do that? Because this is a very broad framework, regularization. Well, there are two main ways. One we can call structural. And in structural regularization, what we do is we do things, we restrict the size or shrink the hypothesis space explicitly. So restricting the sizes of the functions that we can have, restricting the dimension of the space, so things like restricting P, or other controls like something we will look at later, cost complexity pruning. Now, the other type of regularization we can call algorithmic, and this is implicit, so we don't explicitly restrict or reduce the size of the hypothesis space. We do it implicitly, and this is through things like early stopping neural networks, injecting noise into stochastic gradient descent, and other things like pooling and dropout. So what we're going to focus on is the structural type, and in particular norm control. So this involves, as I say, restricting the sizes of the functions that we allow. And how are we going to do this? Well, rather than minimizing our empirical risk over this hypothesis space where we allow any value of theta, we are going to swap this for a minimization over this hypothesis space where we restrict the sizes of the thetas that we allow to within some ball. So this is what we call a ball, because we are saying that all dimensions in the square norm, so this is specifically the square norm, all dimensions, all lengths of each component of this are restricted to some value lambda, right? Their lengths are all restricted to lambda. So we have the equivalent of a circle or a sphere. Now, this, as we know, will be the same as restricting the L2 norm of theta. I've just shown that this is the same or equivalent to restricting the L2 norm of f theta, L2 p of x. So it's the same thing. Now, this problem here, which we can call norm control, so we're controlling the norm of theta, f theta, or equivalently, the norm of theta. We're controlling this to force it to lie inside this ball here. Can be written in a more familiar form. Familiar meaning the way we normally see it is as a penalized form of ERM. So we have ERM, and the regularized form is often in this form, penalized ERM, which is equivalent to restricting the hypothesis space like this. And we do this via Lagrange multipliers, which I'm not going to show you. It's a general way of taking a problem in which we have a constraint, an optimization problem, here a minimization. Here we now have minimize over theta, but with a constraint on theta. We want to turn that into an unconstrained problem by introducing Lagrange multiplier and defining a Lagrangian, which is a new objective function that we want to minimize. And that is this function here. So this function here. So rather than minimizing this subject to this constraint, we can equivalently write it as minimize over all theta this, right, where we have now no constraint over theta. So for each lambda, positive lambda, there will be some capital lambda such that this problem is equivalent to this problem. And this is the form in which we normally see these penal norm control empirical risk minimization formulations. And we're going to take a look at some particular examples. And when it comes to linear regression, the two main ones are ridge and lasso, and those are the two that we're going to focus on. So what will this do? Well, let's think about what we're doing here. First of all, why does this make sense? Well, we are minimizing this, which is what we really want to do. But now we're minimizing this plus this. So we're simultaneously minimizing this and the norm of theta. We want these both to be small. We want small empirical risk and at the same time a small norm of theta, the size of the theta. We want to control its norm or its size. So by going from this, minimizing this, to which we have a quote unquote exact solution to our linear regression problem, we're now adding this term. So what's that going to do? Well, that's going to introduce some error, right? We are artificially adding this term. So we are going to increase the approximation error or model bias, right? That's another way we can look at this. But at the same time, we're going to decrease estimation error or variance. Now, I haven't defined these terms very rigorously here, estimation error and approximation error. But intuitively, we can think of them this way. So this is the error that we incur when we use an estimator or predictor in this case, which is far from the true function. Whereas this estimation error is incurred by the fact that we have a finite number of data points. Now, if we use simpler functions, what will happen? Right? We are less likely to generate a lot of variation in our results. Right? We'll more or less always get the same kind of result. And so what this does, and as I say, we will look at this rigorously later on, where we will rigorously define all of these terms and rigorously define moral complexity, is reduce the the second of these, the estimation error, but increase the approximation error. But we have a trade-off. The idea is that we decrease this estimation error more than we increase the approximation error if we keep this lambda small. So this lambda here is going to be key in all of this as well. And I'm going to write down soon the ridge formulation. So this is the essence of the bias variance trade-off. Or in more formal terms, the approximation estimation error trade-off. So we will study all of these at some point in great detail, but let's just carry on with this for now because I want to introduce ridge regression. Now, most of the classical regularization structures look like this. They're penalized empirical risk minimization. And we can generalize even further. We can say that they all take this form: minimize this plus lambda, some coefficient, some number, times some complexity functional. And what does this complexity functional do? This is some measure of model complexity of our hypothesis space. So when I say most of the classical methods, this includes ridge regression and lasso, which we're going to look at in this part, complexity pruning for trees, smoothing splines, which we will look at later, and even later than that, we will look at reproducing kernel Hilbert spaces. Now, what is overfitting? So I mentioned overfitting and underfitting before, but I didn't really say what they were. Overfitting occurs when our hypothesis class is basically too big relative to how many points we have in our data set, our sample size. So in such cases, what we will have is a large estimation error. Underfitting will happen when the hypothesis class is too small. The functions are too simple to capture the true relationship. So in this case, our model bias or approximation error, I'm using these synonymously, but that's not quite true. But for here, I will use them as synonyms. Our approximation error or bias is large. So overfitting estimation error stroke model variance is big. Underfitting the model bias or approximation error is large. And if our functions are too simple, we get this. If our functions are too complicated, we get this. So if this is our problem, of course, we want to avoid this by not having functions that are too simple, but mainly we're worried about overfitting. The problem is usually not this, the problem is usually this. So the way we can overcome this is by using regularization to penalize highly complex functions. And one way we can do that is by keeping the sizes of the functions that we learn, their norms, within a certain range. And that throws out a lot of more complex functions, keeps them simpler, it biases towards simpler functions. So now we can finally state the form of ridge regression, which is the following. Assume a square loss, and rather than solving the empirical risk minimization problem, which is to minimize this over all theta, we instead minimize this plus lambda times the norm of theta squared. Now, this penalty term here is going to drive the size of theta or norm of theta towards zero. It's going to restrict the size of theta. The strength or the of this penalty, the degree to which we drive values of theta towards zero, will depend on the value we choose for lambda. Lambda is just a number. So do we use 10 to the minus 10, or do we use 0.1 or 10 or 100 or 1,000? That will determine the strength of this penalizing large values of theta. So this also plays a big role, this penalty or regularization coefficient, lambda, which I haven't talked about much so far, but it's important. How do we choose it? Well, in the example that we're going to look at, we're just playing around with values to see what works. But we need principal ways of choosing this, which is what we will look at in the next part, where we will find there are many different ways of choosing this. But the classical way is based on what we call cross-validation. Now, the advantage of this ridge regression form is that we get a closed form solution. What do we need to solve? So we replace the original problem, which is to minimize the empirical risk, which is this, with minimize this plus lambda times norm of theta, the 2 norm of theta squared, which is theta dot theta or theta transpose theta times lambda. So that's what we've got here. Now we can take the gradient with respect to theta. Now I'm just leaving out the subscript theta because it's obvious what we're taking the gradient with respect to. And we can use the chain rule. So last time I expanded all of this out, but we can do it in a simpler way. We take the gradient of this function. Let's treat this as some function of phi. Let's call it psi of theta. And so what we've got is the gradient of psi transpose psi. So we take the gradient with respect to psi, and then we use the chain rule. We take the gradient of psi with respect to theta. And we will end up with this quantity here, plus the gradient of this, which is just 2 times lambda theta. And this has to be 0 at the minimum. And if we rearrange this, we get this solution here, this lovely looking closed form solution. Now, what have we done here? If we compare this to the linear regression or ordinary least square solution, we've gone from phi transpose phi to the minus 1 phi transpose y to now this. And what's the only difference is that we've replaced this with phi transpose phi plus lambda times the identity function. And this is a common way also in numerical computations, matrix that involve matrices, of stabilizing a problem when we have an ill-posed, that should be transposed, ill-posed or ill-conditioned matrix. So phi transpose phi is a matrix. Ill-conditioned means its inverse, it's a square matrix, is unstable. Computation of its inverse is unstable. And that can be for all sorts of reasons. And sometimes when we have that situation, we add some jitter along the diagonal, jitter, or a nugget. It's also called a nugget or jitter along the diagonal. So this is a matrix that will look like this in square matrix. Oh, 2, 3, 4, 2, 3, 4. Right, it's a 4 by 4 matrix, n by n matrix. That's a 4 by 4. Adding a jitter or nugget means adding something along the diagonal, and that's basically some lambda plus, lambda plus, lambda plus. So it makes it more like an identity matrix, in other words. And that's basically what we're doing here. We're adding this lambda I, so we're adding lambda along the diagonal to this matrix, stabilizing it, so that then when we take the inverse of this, we get a much more stable computation. That will introduce error because we're artificially adding this. But if lambda is small, then we don't add too much error, but we stabilize the matrix computation. So there's also that analogy here. Now notice that as lambda goes to 0, we will get back to empirical risk minimization with a square loss. So we just get this goes to 0, we just get this inverse this, which is our empirical risk minimization or ordinary least squares solution. So let's take a look at an example, and we're going to choose the example that we looked at before, 10 points, with standard deviation of 5, and we're going to look at the case with and without regularization via ridge regression. So here is the example, and let's see what's happening. Well, the data points, which are noisy with a standard deviation of 5, are these black points. The true curve we want is this red curve. The blue curve is what happens if we use a degree 9 polynomial. So up terms up to x to the power 9. And you can see we get this wiggling. And this is overfitting. Right? Our model complexity is too high. Our functions are able to adapt to noise too well. So we want to restrict the sorts of functions that we allow to simpler functions. Now, if we use regularization with a value of lambda equal 1, we get this green curve here. Now, you can see it has improved, but not enough. We still get some wiggling, especially here and here. If we go to lambda is 100, we now get a much smoother result, which is much closer to our red curve. So we've solved the problem in some sense. We've prevented these wiggles. We've prevented our overfitting using a very simple adaptation, which is changing this to this plus this. That's all we've done, right? And you see, with just this one small adaptation, we've stabilized our solution and got much more sensible results. And this is what? A few lines of coding. We just define the design matrix, define this in Python, and we perform this. So, by the way, the results, the codes are available look in the description for ridge regression, the ones that generated the results here, and also for linear regression. Both are provided in the respective videos. The ridge regression one in this video. So if you look at the description, you'll find the Python code in there. Now let's look at the sizes of the norms. So this blue one here, the norm of that, the theta that we get is 34.65. This regularized theta has norm 0.45. So you see we have effectively reduced model complexity by restricting the sizes of theta and therefore restricting the norms of the functions. And we've done it very effectively. Now, the last thing I want to discuss in this part is the basis functions and their relationship to the design matrix. So I started out by saying that we are not claiming that these functions that we use are a basis in the formal sense of being linearly independent. So this linear independence of basis functions, even if we assume it, doesn't guarantee that the design matrix will have full column rank. But there are some relationships. So if we assume a Vandermonde matrix, that's one based on monomial, a monomial basis, we do have full rank provided the number of points that we have, data points, is greater than the degree of the polynomial that we assume, and that the points, the xi, are distinct. In that case, we will have, or we will guarantee that the Vandermonde matrix has full column rank. Now, if this is singular, which can happen, linear regression will have infinitely many solutions. The solution will be highly unstable. One advantage of ridge regression, which is connected to what I said earlier about the jitter and the nugget, and now we're going to make it a bit more formal, is that ridge makes this invertible or singular matrix invertible by replacing it with this matrix, adding this term, this matrix, not matrix. So why is this the case? Well, because this matrix is always positive definite, provided lambda is greater than 0. And that fixes our rank deficiency, which fixes the lack of invertibility problem. So let's see why. Let's look at this quantity here. Well, this is equal to, so this we know, this times theta. I've written this before. It's the 2 norm of phi theta squared. And this term here, theta transpose times lambda I theta. Well, the I doesn't change theta transpose. So we just get lambda theta dot theta, which is the norm of theta squared. If lambda is greater than 0, this is only 0 when v equals, sorry, if theta equals 0. I should put theta here, not v. When theta equals 0. Why is that? Well, even if phi is not full column rank, and we can have phi theta equals 0 for theta not equal to the 0 vector. So there are cases where this is 0 even when theta is not the 0 vector. We now have this term here. And if lambda is greater than 0, let's stop worrying about that. This, as long as theta is not 0, will be greater than 0. Right? The norm by definition has to be greater than 0. Right? So it will be 0 only if theta equals 0. And so what do we conclude? Well, we conclude that the kernel of this matrix is the 0 vector. That's the only vector, theta equals 0, such that phi transpose phi plus lambda I theta equals 0. That only happens for theta equals 0. There is no other theta for which that's true. And the kernel of a matrix is defined as those thetas, the set of theta for which this is true. Well, we only have this one. So the kernel is just this one vector 0, which tells us that this exists. In other words, this matrix is invertible. So that's the last thing I wanted to say. After this, we will move on to lasso.